I have to prove this trig identity, and I'm going to start with the left-hand side and try and get to the right-hand side. It's going to be easier to add fractions than to somehow separate 2 cot 2 theta into a couple of fractions. The left-hand side will be equivalent. The first thing, I'm going to put them over a common denominator, so it will be cos 3 theta cos theta plus sine 3 theta sine theta all over sine theta cos theta. It's worth just bearing in mind what 2 cot 2 theta is, especially if you're struggling with this. You can just carry on potentially, but let's just write it down. So it's going to be 2 cos 2 theta over sine 2 theta. Now here are addition formulae. We're going to need them to be able to write them in double angle formulae. And actually one jumps out straight away. We've got cos of something times cos of something else plus sine times sine. That's actually this bottom one here. So this thing here is if I replaced a by 3 theta and b by theta is actually exactly the same as what we've got, which means it's going to be cos 3 theta minus theta. This is in fact cos 2 theta. Okay, and I feel like I've justified it enough here. And then actually sine 2 sine theta cos theta is sine 2 theta. So this is a half sine 2 theta. Okay, and if you're not sure about that one, then let's take the positive one here, replace b by a, we get sine 2 theta is, sorry, sine 2a is sine a cos a plus cos a sine a. That's where the 2 sine a cos a comes from. So my next line can simply be that it's cos 2 theta over a half sine 2 theta. Just going to write that, then I can times top and bottom by 2, 2 cos 2 theta over sine 2 theta. And this is identical to 2 cot 2 theta, which is the right-hand side. And our proof is complete. An alternative strategy for this question would be to actually expand cos 3 theta and sine 3 theta out and simplify it, but it's going to be a lot more effort. It's definitely better to spot that we can actually rewrite it as a double angle. So I'm not even going to do that, but it would get you there. Let's take a look at part B. Not forgetting the identity that we've just shown, actually, because it says hence. That's always a bit of a clue. I just didn't quite enough space, but we need to bring this identity down. Right, so actually I'm solving this equals 4. So using a, it's exactly the same, isn't it? Solve 2 cot 2 theta equals 4. And this implies that cot 2 theta is equal to 2. And now we can just basically swap it around. We can do 1 over cot 2 theta is 1 over 2, which means that tan 2 theta is going to equal a half. That is the equation we're solving here. Now, because theta is between 90 and 180, then 2 theta is going to be between 180 and 360. So that's our extended range. Let's solve for 2 theta. It's going to be inverse tan of a half. So I get 26.565. That's outside the range. I'll reject it in a minute. To get my other ones, let's think about the tan graph. Yeah, actually, so I found out this one here, it repeats every 180 degrees. So I just need to keep adding 180 on. The next one would be 206.565. And this one's in the range, so I'm going to reject this one. And then add on 180 again, it'd be 386. Okay, so that one's actually outside the range. Reject as well. Alternatively, rather than using the graph, you can use your cast diagrams if you like this method. All sausages turn cold. This shows you where each of the sine, cos, and tan are positive. So they're all positive here. I've just worked out this angle. That's the 26.565. The next one, oh, for tan, I'm going down here. And now you can see that it's going to be all the way around. It's going to be that 26.565, and then I'm adding on 180. And then to get the next one, I'd add on 180 again. So it's the same idea. That just leaves us then with theta. And you just need to divide this 206.565 by 2. Which gives me 103.282. Which to one decimal place gives me a single answer, 103.3 degrees. Well done.